exercise 64. So the big question is, what does it mean? To see for two R modules, big M and N, their tensor product as R module is 0. So I'm following Keith Konar's lecture notes on tensor products online. So this is very related with our last exercise. We talk about when the element is small m tensor, small n is 0, right? So now we're asking when the whole R module, big M tensor n is 0. So the answer is very similar. So I will give some sub-exercise to do computations precisely. So the answer is that this tensor product is, as our module is 0 if and only if every bilinear map out of this product of our modules which means any bilinear map from a product n to whatever R module P. Is 0. So bilinear map is 0, which means this maps whatever elements of this product of R modules to 0. So one direction if this is the case, in particular again this canonical one, this is my linear map, is 0. Right? And so this is saying that all the small m tensor are 0, but this is spanned, additively spanned, or see any element is just a finite summation of small elements of this form. So this is consisting of only 0 elements. Conversely, so we have this canonical map gives 0, then any bilinear map to P, so there exists a unique one, make it commutative, and so Mn is mapped to B of Mn, but because of this commutative diagram, this is also tell you that Bmn equals f of m tensor n. F is our linear map of our modules, so this is just f of 0, which is 0, so it maps everything to 0, right? So this is a big picture, nothing too complicated. Well, imagine this can help you to, well, actually it's the same thing, so you know how to do this, right? Sub exercise 1 show that Q tensor over Z with some ring A is 0 when any small element of A has order, finite order. In other words, there is some integer such that it has this torsion. Any element is torsion, Z torsion. Sorry, any element is torsion with some integer. So one possible way is, because we want to check this is totally 0, it's equivalent to check that any bilinear map any z bilinear map to some z module p is 0. Right? So why this is the case? So suppose we have whatever xy. So in particular, y is from a, imply that there exists some integer such that it is killed, y is killed by it, right? And then notice bxy is just b times, let's say, 1 over ny times x and y times y. Because this is by this z semi-bilinear, this is right. I'm kind of rewriting this. Yeah, it's better. So maybe let's don't make it slightly more straightforward. So I'm saying that bxy equals b1xy, but this one is also y1 over yx. So this is again inside q, this is, and so by z bilinear, in particular on the first component is linear, we have this. And then by z bilinear, this is also equal, put it back into the second component. And this is 0, and so this is 0. And so I'll show that whatever element xy, right, it is killed. It is 0. Secondly, so what I want to do, let's first do every particular case and then let's do a general statement. So let's claim again z module are in groups. This is 0 if the greatest common divisor is 1. So the solution is, again, you could use check. Just check the bilinear maps, or small notice, small hint, notice 1 spanned by 1, right? Similarly, and so this implies this is spanned by EIFJ, so tensor 1. So basically, to show this is 0, you only have to check this is 0. This is one way. So another way is, again, let's just check. This is 0 is equivalent to any bilinear maps, bilinear z bilinear maps from z quotient is equivalent b2, whatever p implies this bilinear map is 0. And so the solution is to show this want to show this is the case. So you take any x and y, and you notice that because their greatest divisor is 1, and so b of x, y is actually 1 times bxy, but this is bilinear. I can write 1 as s times a plus t times b. There exists some st integer, right, by disposal formula or something. So, and then by linearity. So firstly, this is in the R module P, and this is just by this R module structure, write it in 2 terms, and then by semi-linearity, you could multiply down the first position or second position, move it inside. So of course I'm moving just A in the first position to kill it, and moves B to the second position to kill it, and so both equal 0, so this is 0. Okay, with very similar argument here, you just have to see that 1 tensor 1 is actually the same as, so SA plus TB 1 tensor 1, and then this is A tensor 1 and S, this is 0, plus T tensor 1 tensor B, this is also 0, and so this is 0. So either way works. Okay. So the last sub exercise, actually this is a theorem in Connor's notes for A, B integers with D their greatest common divisor. So stronger than the last exercise we just proved. We want to ask you to prove that, which is most general argument of this type. So I'm going to ask you to prove the tensor product of general AB is isomorphic to Z quotient by D. Okay, so firstly notice that again this spans our Z module, and so at the Z module you have to check its order. Similar as before, so D times 1 tensor 1 is 0, implies that the cardinality of this Z module should be less equal than D. And secondly, conversely, we can construct a map, Z linear map from this ring we want to the quotient D, and I want to show it's surjective. So of course, anyway, you want to construct a map from a tensor product to a module, you have to use universal property. So we firstly construct what is a bilinear map in a very natural way. You have x and y, you map it to x times y, and then take its image after the quotient by D, because D divides A and D divides B. This is well-defined ring, our linear map. And so once check this is bilinear, it's obvious, and then canonical map tells you that there exists a map such that this is commutative, so which means there exists a mapping x tensor y to x y bar. And to show this is surjective, just notice that the x tensor 1 is mapped to x bar for any x in z, right? And so this is surjective. And so the cardinality is bigger or equal than d. This implies cardinality equals d.